Okay. Yeah. Good afternoon, everyone. Welcome to this live session on 10/12/2025. Okay. So in the previous live session, okay, so we have solved some of the problems in state space analysis, like finding the given the state space model of a system. So we have seen problems on finding the state transition matrix, the transfer function, and solution for the system of equations. Okay, so x of t. So now in today's live session, what we see is we are going to see the controllability, observability, and the technique called pole placement technique. Okay, so basically these two controllability and observability. Okay, so uh, these are the two aspects in the state space analysis. So they actually talks about they are very crucial in deciding the existence of the solution for the optimal control problem. So when you see this controllability, so it will related to the existence of the solutions for a in state feedback form. Okay, suppose if you wanted to place the poles at a particular place, so the first notion you need is the controllability. Similarly, here in controllability, what we do is something called as the state feedback. That means we directly take these states and use those states for finding the control input. Whereas in some of the practical systems where the states may not be available, in that case, so we need to either observe or the estimate the states. So which is most important? And the states are directly available. So we will observe or estimate the states, and then after that part, we will use the we will give that state to the state feedback system. Okay, so so the controllability and observability are very important notions. Okay, so here you can see the first image and second image. First image related to the state feedback, where what we are doing is here the states are available. Let's say X. That states we are taking in the this way and multiplying with this gain F and passing here to this summing point and then finding this U. Okay, so that U will be something like R of t minus F x of t. Okay, so you are using the states and feeding them to finding the input. Okay, so that is one way. The other way is here sometimes the states may not be directly available to you. In that case, what you do is you will use this observer and find this state estimation. So you estimate these states, that's why we are calling x cap instead of x. Then we will find this u of t as r of t minus f x cap, where here x cap is the estimated state. It means that so observer is used for estimating the states. So that we call it is as uh, output feedback and observer. Here it is state feedback. Okay. So 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 as I said, the input is r of t minus f x of t. So in this, if you substitute u of t in this expression, so these are the closed loop dynamics. Closed loop dynamics. Here, this is called as the uh, closed loop A matrix. Okay, closed loop A matrix. What is our requirement for the closed loop systems to be stable? The eigenvalues of this ACL must be negative. Then only the system goes to stability. Okay, so here, so that is the major aspect. So here what we do is we can use this f. Okay, we can properly design this f in such a way that we can place the poles to our desired locations. So this method of placing the poles wherever we want is called as the pole placement technique. So in some cases, when this x of t is not directly available, this x of t, so we need an observer. So using that observer where we don't have the states directly, okay, we might only have the outputs. Okay, from the outputs, we wanted to calculate or estimate the states. Outputs are measurements. Okay, so from the measurements, we calculate our states or estimate the states x cap. So we get the states from the outputs. So this process is called as the observation or observer design. Okay, so let's go one by one. First step is the state controllability. So the general definition for state controllability of a given system of state space model for a system is this. Okay, so you can read this. The state X is said to be controllable at t is equal to t naught. T naught is the initial state. If there exists a piecewise continuous input u of t, if there exists a piecewise continuous input v of t, which drives the system from initial state t naught to final state tf within the this finite time tf minus t naught is greater than or equal to 0. Then we can say that this x of t of the system is controllable in this finite time. Okay, so the total we can say system is state controllable. So in short words, if you started the system at t is equal to t naught, okay, if there exists a input of u of t, which can takes the system from t naught to tf, which is a finite time, then we can say that the system is controllable at uh, at t is equal to t naught. Okay, so that is the definition of the controllability. Okay, so that is first part. So the in general for any system x dot is equal to ax plus bu, we can check system is controllable or not using this matrix. Okay, so LTA system is controllable if this matrix given A and B matrices, if this matrix has full rank of n. Okay, we can say that system is controllable, or you can say that AB pair is controllable. Okay, so we can easily check if the rank is within the rank n is equal to 3. Okay, so this is first definition. Is there any doubt? So I suggest you to go for the proof in the video lectures how this S matrix came and why it is and why system is controllable if the rank is n. Okay, so but this is the basic definition. From this definition we will be get to this S matrix and try to show rank is equal to n. Okay, so that is called as the controllability. So for example, if we have A matrix and B matrix, so here S matrix is nothing but what? So B, A, B, etc. Sorry, B, A, B, A square, B, etc. A power n minus 1, B. So here n is nothing but n by n is nothing but 2 by 2. So n is equal to 2. Okay, so n is equal to 2 means what you will be having till these two terms only. Okay, if you find this 1 minus 2 0 0. Okay, so if you find the det, okay, so det of s, okay, that will be 0. When det is equal to 0, the rank of s will be less than 2. Okay, here in this case rank of s is 1, which is not equivalent to 2. Okay, hence s is not invertible, so that is uncontrollable. Okay, are there any queries as of now? Any doubt or query? Any doubts? Okay, so we can also check the same thing using this similarity transformation. So with similarity transformation is given this system, So let us define a new state variable y is equal to px. Okay, then y dot is px dot. You can substitute x dot expression here. So you can write this y dot. So y dot is equivalent to a y plus by u. Okay, so we have transformed this system to this system using this suitable transformation matrix P, where P inverse should exist. P inverse will exist. Okay, so you can directly take any P matrix where P inverse is existed. You can calculate the these terms. You can calculate these terms. Okay, so then you can given state space system, you can write it like this. Okay, here you can observe that the input is directly uh, affects the y1. It will not affect the y2 because of z0. It means that only some states here y1 states is controllable. You can control it through u, whereas y2 you cannot control. Okay, so hence the system is uncontrollable. This is another method. Okay, so let's get to the observability. So observability again. So we have the system of equations. Okay, so system is completely observable if every state variable of the system affects some of the outputs. System is completely observable if every state variable of the system affects some of the outputs. So again, this is the basic definition. Okay, where this definition says that this particular state, initial state, is observable. Observable means what? This is we can possible to estimate. Possible to estimate in another meaning. Okay, this x of t naught is observable for any input u of t. Okay, for any given input u of t, there exists finite time tf is greater than or equal to t0, such that the knowledge of u, knowledge of matrices abd, knowledge of output, they are enough to determine this x of t naught. Okay, so it means that this x of t naught is observable, okay, for any given u naught. Okay, so the knowledge of u abcd matrices, okay, and output c, these are enough to find x of t naught. Then we can say that this x of t naught is observable. Okay, if every state of the system is observable, then we can say that the whole system is completely observable or simply observable. Okay, I hope this definition is clear here. So this gives us the notion for possibility of estimating the state x of t naught, any state at its initial value. Similarly, this is the general intuitive definition. Again, if we start from there, this is the condition. Okay, given a b c a b d e matrices. Okay, so just by using a and d, we have the condition for, or we have the we can check the observability of the system. Okay, you can check the observability of the system just by finding this matrix. Okay, and its rank, and its rank. I'm sorry, just a minute. Okay, what is happening? Yeah, so and its rank. Just give me a minute. Okay, so we could check. Sorry, pen is giving the issue. Just give me a minute. Do you have any queries as of now? So the definitions of observability and controllability. You have any queries?
No, sir.
Yeah, I think pen got stuck.
Sir, check its charge. It's charge discharge, I guess. Your pen.
No, no, no. It's completely charged.
Okay.
It's fully charged. I've kept it charging for now only. It's fully charged. Yeah, I think I'm getting some issue. Okay, fine. So this is the condition. Uh, can you just give me 5 minutes? I'll try to restart and come back. Maybe
Yes, sir.
due to that issue, it's not working. Okay, just give me 5 minutes. Yeah. Can you hear my voice now?
Yes, sir.
Yes, okay. So this is the condition. So again, please go back and see the video how we got this V matrix. Okay. So from this definition, this is the basic definition, intuitive definition you should remember for observability of a system. Okay. So what we will do now is we'll do some of the problems to understand what exactly the meaning of observability. Okay, so let's start quickly. Okay, so let's say a system is given x dot is equal to -6 -5. Okay, so 1 0 x plus 1 0 u. Okay, and y is equal to 3 1 x. Okay, so we need to check the controllability and observability. So first, okay, so this is A matrix, B matrix, and C matrix. T is 0. Okay, so first, so observe controllability. So controllability we could be written as S matrix, or you can say controllability matrix is C matrix. Okay, the basic condition is B, A square, B, etc. A power n minus 1. B, where n is nothing but this order, where here n is equal to 2. So in this case, the C is nothing but n minus 1, 2 minus 1. So that is 1. So that will be as B, A, B. So we have this B matrix. So then we can write AB as minus 6 minus 5 1 0, B as 1 0. Okay, so we'll be getting minus 6 here, 1 here. Okay, then C matrix is, so C matrix is B AB 1 0 minus 6 1. Okay, now if you take the det of C, okay, you'll get 1 minus 0, which is 1. Okay, det is not equivalent to 0. Since det is not equivalent to 0, so the rank of C is 2, which is nothing but the full rank. Okay, hence the system is controllable. Okay, so this is how we will check the controllability of the matrix, controllability of the system. Okay, next let us see the observability. Observability, let's say we have to find the O matrix. Okay, so which is nothing but, so the matrix C transpose A transpose T transpose etc. A transpose whole power n C transpose. So this is the matrix. So here in this case, since n is equal to 2, okay, so here, so we'll get C transpose A transpose C transpose. Okay, so A transpose C transpose we have to find, where A transpose is nothing but A is given as minus 6 minus 5 1 0. So minus 6 uh, minus 5 1 0. This is A transpose. And C is given as 3 comma 1. So hence it is 3 comma 1. Okay, so then we'll have minus 18 plus 1 minus 17. Here this would be like minus 15. Okay, so now the O matrix is C transpose 3 1 minus 17 minus 15. Okay, so now if you take the det of O, so that will be like, so 3 into minus 15 minus 17 multiplied 1. Okay, so that is like minus 28, which is not equivalent to 0. Hence the system is observable. System is observable. Is this clear? How we are checking the observability and controllability? Is this clear? Any
Yes,
doubt?
sir.
So this is the condition. This matrix, controllability matrix.
How we came to BAB and not that A square B and till A to the power n minus 1B?
This derivation you are asking,
Um, um,
correct?
what's the order of A? Like the highest order of A, we took 1. So how
No,
we
no,
took
order
order?
is 2 by 2 here. N by
Huh.
n is 2. So
Hmm.
2 minus 1 is 1. So that's why maximum is AB.
Okay, okay, okay.
Okay,
That's
so this is called as the controllability matrix, whereas this is called as the observability matrix. Okay, for any given system, we will check
y is 1
first
into 2, no? Say y equals to that 3 1 is 1 into 2 matrix, no?
which one.
Oh,
This
sorry.
one.
A. Okay, sorry. Yeah, A is 2 into 2. A is 2 into 2.
Okay, yeah. So controllability and then observability. Okay, so that is how we will check. First, you will write the controllability matrix and observability matrix and check their delt for checking the rank. Here, there since data is not equivalent to 0, it's full rank. If it is full rank, observable. If it is full rank here, controllable. That's the indication. Okay, next. We'll see one or two problems and then we'll go to the pole placement. So next example. So let's say for an LTI system, the transfer function is given to us. H of s is s plus 3 divided by s plus 1 S plus 2, S plus 3. Okay, let's say. So there is a pole and there is a 0 at the same location, that is S is equal to minus 3. Okay, so now let's say this can be written as, so S square plus 6, S square plus 11S plus 6. If you multiply these all the denominator factors. So now whenever a transfer function is given to you, okay, so we can write this CCF form. Okay, so canonical controller control form, canonical control form. Okay, so CCF form would looks like this: x1 dot, x2 dot, x3 dot, three state variables, and A matrix is should be 3 by 3, and here we'll have x1, x2, x3 plus the input is u. Okay, so similarly y is, so we can write like this: x1, x2, x3. Okay, so in CCF form, what we do is we directly take these coefficients. Based upon those coefficients, we directly write the A matrix. Here in this case, the last coefficient, the next coefficient, and then next coefficient, and then 1. Okay, so the next terms are 1 0 0, 0 1 0, 0 0, and the C matrix will be based upon the numerator 0 1 3. Okay, I hope this is clear. Okay, whenever a transfer function is given to us, we could write the directly the state space form from transfer function to state space. So this is transfer function, this is state space, just by observing the transfer function. Okay, so we take these coefficients into A matrix, and we take these coefficients into the C matrix, then you will have the B matrix. So this is A matrix, B matrix, C matrix. Is this clear? Is this clear? Okay, so here A matrix is, let me write down, A matrix, B matrix, and C matrix. So A matrix is -6, -11, -6, 1 0 0, 0 1 0. This is A matrix from here. Next B matrix is 1 0 0. Next C matrix is 0 1 3. Okay, so now we will write down the controllability matrix as C, controllability matrix as, so B A B A square B. Why till A square B only? You can check in the previous problem. So here previously this is 2 by 2. So 2 minus 1, that is 1, AB. Now in our problem that is 3 by 3. Okay, so that's why it is A square B. Let me write there matrix. So this will be etc. A power n minus 1 multiplied B. Okay, here, so n is equal to 3. Why is n is equal to 3? Because A is 3 by 3 matrix. Okay, hence C is what? B A B A square B. Is this clear? So using this A and B, we can calculate the C matrix. I'm giving that matrix directly. 1 minus 6, 25. Please calculate them and verify. 0 1 minus 6, 0 0 1. Okay, so that is first matrix, which is called as the controllability matrix. Okay, so now if you find the det of C, if you find the det of C, okay, so that will be like 1, 1 minus 0, so plus 6, 1 minus, sorry, so that is 0 minus 0 plus 25, 0 minus 0. Okay, so that you are getting as 1. Okay, so which is not equal to 0. That means what? The rank is 3, which is nothing but 3, which is nothing but full rank. Okay, since that is full rank, so given system is controllable. Given system is controllable. Is this clear? Next, is there any query here? Is there any query here?
No, sir.
Yeah. So next, similarly, what we do is we will find the observability. Okay, so observability matrix. Okay, so O, that is nothing but uh, observability matrix is A transpose. You can check the formula again. So sorry, C transpose. So C transpose, A transpose, C transpose, etc. A transpose whole power n minus 1 C transpose. Here n is equal to again 3. So that will be C transpose, A transpose, C transpose, A transpose whole square, C transpose. Since you know A matrix, you know the A matrix, C matrix, you can easily find this O matrix that I am giving it directly. So 0, 1, 3, 1, 3, 0, minus 3, minus 11, minus 6. So please verify this. Okay. So now if you find the data of O, so what do you get? 0, 18 minus 0, minus 1, minus 11 plus 9, plus 3, minus 11 plus 9. Okay. In this case, what is our answer? Here, the first term is 0. So the second terms, what do you see? Are we getting data as 0? I think that we are getting as 0. Is it correct? Second term, so 0. This has to be, just a minute, just a minute. So this is minus 18, minus 0, minus 1 multiplied, minus 6, minus 0. Third one is plus 3 minus 11 plus 9. Okay, so that will be 0. Hence, so the rank is, okay, less than 3, because that is equal to 0. Since rank is less than 3, so system is what? Unobservable. Is there any doubt in this? System is unobservable. Is there any doubt?
No, sir.
Yeah. So now from here, system is controllable. Okay, and system is unobservable. Now go back to the transfer function. Okay, so consider this transfer function. What do we have? Okay, so if you see this transfer function, so now if you compare the poles and zeros, okay, so the basic reason for the observability unobservability is that, so if you compare these two, so this pole and this zero and pole gets cancelled. It means that there is a pole zero cancellation. Okay, so whenever there is a pore zero cancellation, that will affect the system controllability and observability. So now what is our transfer function looks like? So we can call that is as a reduced transfer function. Okay, so which is the 1 by s plus 1, 1 by s plus 2, which is equivalent to 1 by s square 3s plus 2. Okay, so in general, these kind of systems, we can write it is as x1 dot x2 dot into the directly CCF form, canonical controllable form. Okay, so as this, can write it is as 1 0 minus 2 minus 3 x1 x2 plus 0 1 u. Okay, similarly y as 0 1 x1 x2. Okay, so it means that simply what we do, so just by observing the transfer function, we take these coefficients are here. Okay, and by observing the numerator, we take those coefficients are here. So this is called as the controllable canonical form. Okay, so again, if you find the because you have now A matrix, B matrix, C matrix. Okay, so now if you find the controllability matrix, it will be as BEAB because it is 2 by 2 now. Okay, so what do we get? We get the controllability matrix as 1 minus 2 0 1. Okay, so similarly, we get the observability matrix as C transpose A transpose C transpose as 0 1 1 0. Please check these values. Okay, so we have these two values. Okay, now you see what is the det of C? Det of C is 1 minus 0, so which is not equivalent to 0. What is the det of O? So det of OE is nothing but 0 minus 1, which is not equivalent to 0. Okay, so now what does it mean? System is, because the det is not equivalent to 0. Okay, so hence rank is full rank. Rank is full rank. That means system is controllable and observable. System is controllable and observable. Is this clear? So what is the meaning here? If you see the problem, okay. So a system is given to us with three, this is S cube, with the three state variables, correct?
Yes, sir.
N is equal to 3. When n is equal to 3, same system is controllable but not observable, correct? Not
Yes.
observable. Whereas when pole cancellation takes place, system order reduced to 2 by 2. From n is equal to 3, it reduces to n is equal to 2, correct? When system is order gets reduced, it is becoming controllable as well as the observable. It means that the reduced system is preferred compared to the higher order system. So that's the observation here. Is that clear?
Yes, sir.
Okay. Any queries here? Okay. So this is how we can check. Given the state space systems, you can check both controllability and observability. Okay. Next. So next, we'll do the content revisiting of pole placement technique quickly. Yeah. So, so regularly we know that The location of poles decides the stability. Okay, so generally what we do when we designed the controller, PID controllers, compensators, etc. So when the system is stable, we wanted to move the root locus, and we wanted to change the behavior of the Bode plot in such a way that the unstable poles, stable poles, we wanted to move them to stable poles. Correct. So also the location of poles is the concept of location of poles is very important, because they tells us about the transient response. Also, they will inform us about the settling time, overshoot, etc. Okay, so here the point is, can we design a controller? Okay, so which will place the poles at our desired locations. Because so once a system is given, you know the poles location, you wanted to move them to the stable side. Okay, so the main question is, can we design any controller, okay, which will help us to place the poles at the desired locations? That designing of that controller is called as the pole placement technique. Okay, so it will give us flexibility to place the poles, closed loop poles, to our desired locations. Okay, so here the just now we saw that, so AB is controllable, or matrix C is full rank. Okay, so these are the notions of the controllability, which this one is also called as the Kalman rank condition. It means that if the rank is full, we say that system is fully controllable. Okay, when the system is fully controllable, only we can go for designing this pole placement control technique, pole placement control design. So before going for the pole placement design, our first step is to check whether the system is controllable or not. Okay, then all these states must be available for the feedback. Okay, third one is, we should not have any constraints on the input signal. Is this clear? So first we need to check system is controllable or not. Once the system is controllable, only we can go for designing the pole placement. Second is, all the states must be available to us. Third is, the input u of t must not have any limitations, or any constraints. Okay, so if you see our previous compensator design and controller design, basically what we saw was uh, a maximum overshoot given to us, a settling time given to us. Using those peak overshoot and settling time, we find this omega n and zeta. Once we find omega and zeta, using this equation, substitute them in this equation, okay, and find the roots. We call them as what? We call them as dominant poles. Okay, so once we know the dominant poles, we can place the rest of the poles. Okay, if the dominant poles are here, okay, we can place the rest of the poles in this side. Okay, somewhere here, so that they move very fastly than these dominant poles. Is that clear? That's what the previously we have followed, classical approach. Now here what we do is a little different. Okay, so let's see what exactly this pole placement control design technique is. So firstly, this is our state space model. X dot is equal to ax plus bu. Okay, so the control input we take it is as u is equal to minus kx, which we call it is as a state feedback form. It means that we are taking the state and feeding back to the input. Is this clear? This is important. Okay, now if you substitute this u is equal to minus kx into this equation, so how that would become? X dot is equal to ax plus bu, b into minus kx. So that can be written as a minus bkx. Okay, so which is equivalent to this. Okay, so that is nothing but this one is ACL X, closed loop system dynamics, closed loop system A matrix. Okay, so now the objective is we need to design this K matrix in such a way that if you take the characteristic equation, characteristic polynomial, okay, characteristic polynomial of A matrix is nothing but what? Si minus A, det. Okay, here characteristic polynomial of closed loop system is nothing but what? This one, Si A minus Bk, that has to be equivalent to S minus mu1, S minus mu2, etc. S minus mu1, where these mu1, mu2, mu1 are the desired pole location. Is this clear? You can see this example. Okay, so these are the steps. First, we check the controllability. Assume k is equal to k1, k2, k3. Then substitute into this. So compare them, compare the coefficients with equal power. Then solve for k1, k2, k3. You can see this example. Okay, so first characteristic equation is given. It means that x dot is equal to ax plus bu is given to you. Okay, if you take si minus a det equal to 0. Okay, so that has lead to this s cube 6s square plus 11s plus 6 equal to 0. This we call it is as a characteristic equation. Okay, so this for this roots are s is equal to minus 1, s is equal to minus 3, s is equal to minus 3. That means the roots are minus 1, minus 2, minus 3. Okay, now you wanted to place our roots minus 1, minus 2, minus 2 only. That means you wanted to place the rules here. That means you wanted to move this third root to this location. Is this clear? Is this clear? So the red are the desired, the blue are the existing. Okay. So what do we do?
Yes.
We take this Si minus A minus Bk, where A minus Bk is the closed loop system, where K is this. Okay. So we found this characteristic polynomial. Okay. Now our roots are S is equal to minus 1, minus 2, minus 2. These are our desired. So what do we do? Desired polynomial S minus 1 here. S is equal to minus 1, minus 2, minus 2. So desired is S minus 1, sorry, S plus 1, S plus 2, S plus 2 equal to 0. So you'll get this. Okay. Now what you do? You compare this polynomial with this polynomial. Okay. So what are you going to get? So if you do the comparison, 6 plus k1 equal to 5, 11 plus k2 equal to 8, 6 plus k3 equal to 4. What do we get? K3 as minus 2 from here, k2 as minus 3 from here, k1 as minus 1. This one. Is this clear? Is this clear?
Yes, sir.
So simply first this is the given. Okay, these are the desired poles. Okay, so
Blue one is
now
given and red is desired, no?
yeah.
Huh.
Blue one is given, the red are desired. Okay, we wanted to design K in such a way that the closed loop system should have these red poles.
That minus
Okay,
3 will jump to minus 2 itself.
yes. Now
Hmm.
if you have this K matrix. Okay, in
Hmm.
this K matrix, what is the control law you have considered? U is equal to minus Kx, correct? This one, if you substitute here, what do you get? What will you get?
Minus The
So
x
this one,
value
if you substitute, x dot is equal to ax plus
equals
b
to
minus kx, correct? This is nothing but what? This is nothing but, just a minute.
u equals yeah.
This is nothing but minus k, k1, k2, k3. Okay, multiplied x1, x2, x3. Okay, so that is nothing but k1, k2 is minus 3, minus 3, minus 2. So minus of minus 1, minus 3, minus 2 multiplied by x1, x2, x3. So what is the control law?
K
x1
minus
plus
k.
3x2 plus 2x3. That is the control law.
Okay, got it.
Okay, so this control law, if you apply, your system will move from blue poles to the red poles.
So total number of poles becomes then two now.
No,
But
no, three
order,
only. Three only,
but
repeated
order
poles
of
at
the,
two.
okay. There are two poles at minus two then.
Yes, yes, repeated poles.
Hmm.
Okay, this is
Yes.
basic technique. This is basic technique of pole placement design. Okay,
Achha.
next. Next method
From
is
where we
using
got
this.
that
Yeah.
u equals to minus kx?
What is it? U is equal to.
U equals to minus kx. From where we got that?
This is what the control input we take.
So it could be changed or universally or for every
No,
question we.
universally same, minus kx only. We should not take u is equal to kx. Why? Because if you take u is equal to kx, it will become positive, this term.
Huh.
If this one
Yes.
becomes positive, so let's say starting is given to you as x dot is equal to ax plus bu. Okay.
Hmm.
If A is stable matrix, it means that all its eigenvalues are negative. Okay. In
Hmm.
case if you take u is equal to kx, this one becomes positive, a plus bk.
A plus bk.
So yes, that bk term, by adding positive term, it will try to make those eigenvalues, it will try to take the eigenvalues towards RHS side.
Okay. Okay. Okay.
Okay, so if you take negative, they'll try to put the whole eigenvalues of this
Stable. If
term
we take positive, it
negative.
became unstable.
Yes, yes, exactly.
Okay.
So for stability, we take u is equal to minus kx,
Minus
not,
kx.
yeah, not u is equal to kx.
Okay.
Okay, so that's how we take. For every controller, we take u is equal to
U
minus
equals
kx.
to minus kx. It's
Yes,
state feedback formula.
yes, yes. So that is
Okay.
first thing. Next thing is we use this controllable canonical form. Okay, so as I told you, controllable canonical form is this. Okay, simply we take the numerator coefficients here. Okay, so as usual, we have state model, control law, okay, K matrix. Okay, so now what we do, substitute this A matrix, K matrix into this equation along with this U. Okay, so you will get this ACL is equal to A minus PK. So if you see this A minus PK term, it looks like this.
Hmm.
A matrix, B matrix, and K matrix. Okay, now you have these terms. Okay, so that is first thing. Second thing is, let's say these are your desired poles. Okay, then what is the denominator? S minus mu1, S minus mu2, etc. S minus mu n. Okay, if
Hmm.
you expand them, you'll get this polynomial. Correct? You'll get this polynomial. Now, these polynomial, these coefficients are going to be equivalent to these terms because this is the closed loop system. Okay, and these are the desired poles you want. Okay, so now if you equate each of these terms with these terms, okay, you can see here you will be getting your k1, k2, etc., k etc., other values. Is this clear?
Hmm. Yes.
So if your system is in the canonical form, that means your A matrix will looks like this.
Hmm.
Okay, so directly you are getting your k1, k2 matrices, k1, k2 values in terms of the, this comes from the desired, this comes from the A matrix. You can see here. Okay, so suppose you can see here in the example, again this one, when you take Si minus A det equal to 0, characteristic equation. Okay, so from the characteristic equation, that is the denominator, these are the coefficients. Okay, A0, A2 is 5, A1 is 8, A0 is 4. Now these are the desired poles. Okay, lambda 1 is -1, -2, -3. Okay, characteristic equation you will find like s plus 1, s plus 2, s plus 3. So this is the polynomial. Okay, these are the values. Okay, so these are the alpha 1, alpha 2, alpha 3. Okay, so this is alpha 2, alpha sorry, this is alpha 1 and alpha 0. Let me write it again. This is alpha 2, alpha 1, alpha 0. Now we have alphas, you have A's. Alpha I you have, AI you have. So you can find your K1, K2, K3 simply by subtracting alphas and K's. Is this clear? This is your K matrix. Is this clear? So this is another way. If you are given A matrix is in the controllable canonical form. Controllable canonical form means simply you have these coefficients here. The rest of the terms are like this. Okay, so in a proper way, 0, 1, 0, 0, etc. 0, 0, 1, 0, 0, etc. 0, 0, 0, 1, last term is 0. Last term is 1. Okay, so this is called as the controllable canonical form. Suppose if the A matrix is not in the canonical form, if the A matrix is not in the canonical form, so in that case, what you do is, you can check this one. So let's say what we do is we have x dot is equal to ax plus bu. Okay, so let's say we are taking a new state variable which is z. Okay, we take x is equal to pz, where p is the transformation matrix. P is the transformation matrix. So from here we can find z, which is nothing but p inverse x. For p inverse should exist, then you take the derivative, z dot is equal to p inverse x dot. Then so z dot is equal to x dot, you know already, that is ax plus bu. So you will get p inverse ax plus p inverse b, and x is nothing but what? Pz, that you will substitute here. Okay, then you can write z dot is equal to these three terms put together, az, these two terms bz. So finally what you are getting is z dot equivalent to azz plus bzu. Okay, so you have started here. Okay, you have started here, used this transformation and ended up like this. Is this clear? So you have transformed your state space model using this transformation matrix P, converted to a new transformation, new state space model. Is it clear? Okay, so now in the basic state equation, you have A matrix. Now in the converted, you have AZ, which is nothing but P inverse AP. So if you find the eigenvalues, both eigenvalues will be same. Both eigenvalues will be same. That is what is called as the similarity transformation. Is this clear? Any queries here?
No, sir.
So you are starting with basic state space model using the transformation matrix P, and do these simplifications. You are ending with this. Okay, so transformation. So the eigenvalues of A exactly equivalent to eigenvalues of AZ.
So that relation is actually that capital omega
This
relation
meeting
between
is being
capital omega
publicly
and small
streamed.
omega, right?
Sorry,
TFT.
hello. Okay, so the transformation matrix P we would be writing as P is equal to CW. Okay, where C is nothing but the controllability matrix. So W is of this form. So we get this matrix P. Is this clear now? Okay, so then we have this Si minus A polynomial. Okay, so we have this Z dot state space model. Okay, so if P is completely invertible, okay, so we are writing the new state space model like this. Okay, so in this method, what we do is now we have this new state space model. When we have this new state space model, this one, now we can do the pole placement design just like previous one. What we do in the same way, we choose u is equal to minus kx. Here what is it we choose? Minus kz z. Okay, from there once we got our kz using our regular method 1. Okay, so the now we can find our k like this. Is this clear? Is this clear? Any query here? Any query?
No, sir.
Yeah, so simply what we are doing is, so we are choosing this transformation matrix P using this controllability matrix and W matrix, converting the given x dot is equal to x plus du using this transformation into new state model with z as the state variable. Okay, once we have this equation directly, like method 1, we are designing the pole placement technique controller. So that is nothing but minus kz. Okay, then we can find the k matrix. K matrix is the controller for the basic state space model. Okay, you can see this example. We'll see in an example. The that is the second one. The third one is we know that a cap is equal to a minus bk. Okay, so if you find the characteristic equation as Si minus this matrix a cap. Okay, so these are the this is the equation. Okay, if you expand it, you'll be getting alpha 1, alpha 2, etc., alpha n. Okay, now what is this Cayley-Hamiltonian theorem says? Okay, so let's say if we have that is also called as CH theorem. Okay, so if you find the characteristic equation of A, what is this? Si minus A det equal to 0. Okay, what is that equation we will get here? We will get something like some a naught plus a1 a sorry a1 delta plus a2 delta square etc plus a sorry, these should be yes. Let's say if you take a delta, what is this characteristic polynomial? We will get a naught plus a1 delta 1 delta plus a2 delta square etc. At last we will get an delta n. Okay, so the Cayley-Hamiltonian theorem says that that is equivalent to a naught plus a1 a plus a2 a square plus etc plus an a power n. This is what the Cayley-Hamiltonian theorem says. It means that, so when you take characteristic equation lambda I minus a, that is what this equation says. Okay, The Cayley-Hamiltonian theorem says that in place of lambda, if we substitute A matrix, that also will be equivalent to 0. Is this clear? So every A satisfies its own characteristic equation. Okay, so that means this is the characteristic equation for this is the characteristic equation of Si minus A cap. Okay, is equal to 0. Once we have this characteristic equation, that will be satisfied by A matrix itself. Okay, so that's what the Cayley-Hamiltonian theorem says. Okay, so now you can see if you take for n is equal to 3. Okay, we wanted to check for n is equal to 3 only. So a cap square, a cap cube. Okay, so this is what the characteristic polynomial. This is what the characteristic polynomial. So that is Si minus a cap. Okay, in this substitute a cap square, a cap cube. Okay, you'll get this equation. Okay, once you have that equation, so you know that from the Cayley-Hamiltonian theorem, you know this result. Okay, please substitute, you'll get the final equation. Okay, you have to write and check. So from this, you can see here, you're bringing this one this side. Okay, so you have this equation. You're getting the inverse. So now if you multiply both sides, because what you want is you wanted to find matrix K. Okay, what do we do? Simply multiply with 0, 1, 1, which makes this term 0. So which makes this term also 0. Only K will be left. Okay, finally, K matrix is nothing but what? This one. 0, 0, 1. This is what? This is your controllability matrix. And this is the characteristic polynomial. Is this clear? Characteristic polynomial is this. Is this clear?
Yes,
Yeah.
sir.
Now you can see the example. Okay, A matrix is given, B matrix is given. Okay, so this is what the control law we wanted to use. Okay, the desired poles are at -2 plus or minus A4, -2 minus A4, S is equal to -10. These are the desired polynomials. Okay, so controllability matrix you will find. Okay, so which we got as this one. Okay, rank is C, rank is 3. So system is controllable. Okay, so first what we saw in method 1, what we do. So this is the characteristic equation we have. These are the coefficients. Okay, desired polynomial. Desired polynomial is nothing but S minus of -2 plus J4. This is first one. S minus of -2 minus J4 S plus 10 equal to 0. Okay, if you calculate them, you are getting this. Okay, so you got alpha 1, alpha 2, alpha 3. Okay, so using method 1, you can find the K as 199.55.8. Okay, I hope this is clear. This is method 1. Next, using method 2. So method 2, what we do? So you have A, B, K matrix. Okay, you have these coefficients. This is the desired. So you compare the coefficients. Comparing what? Comparing 6 plus K3 equal to 14, 5 plus K2 equal to 60, 1 plus K1 equal to 200. So solving those, you'll get 199.55.8. This is method 2. Is this clear? Next method 3. Okay, so we have seen this is what the Ackermann formula we got. Okay, what do you need here? First is pi a. Pi a is nothing but what? So A matrix characteristic equation. So this is nothing but Si minus A. Okay, so this is pi of A. Okay, so you got pi of A as this. Okay, next this is the controllability matrix we get calculated. So you can find the K as 199.55.8 with the calculations. Is this clear? This is method 3. Okay, so you can also use the
Hmm.
MATLAB to calculate that. Is there
Yes,
any
I will.
doubt in these three methods?
Just only the but writing that BAB, there is a three dots separating. It's not a matrix.
No, it is a matrix. This each one is a column.
Like 001 is there. It's a 3 into 1. Sorry, 1 into 3 matrix. So this is also 1 into 3 matrix with its inverse.
Which one? This is each one is a column. So this is B, this is
Okay, okay.
AB.
B is a
This
separate
is A
column,
square.
AB is a separate column, and A square B is a
Yes, yes, yes,
separate
yes,
column.
yes,
Okay.
yes, yes,
And
yes.
how we get this A cube plus 14A square
This
from the
one.
previous?
Yeah, this
Huh,
equation only.
this equation, matlab that phi A, how we getting?
Phi A means just a minute. Yeah, here you can see
Oh my.
this phi A. Okay, so what you do is simply find the this equation first. This equation is nothing but Si minus A. Okay,
Huh, huh. And
so
this is
once
not A, this is A with the
no,
tilde.
you find delta I minus A. Okay,
Huh, okay.
so
Acha, with
you
S it's we will write tilde. Okay.
once you get that,
Hmm.
you will be
Huh,
getting in terms of delta. Okay,
huh. Yes.
just replace delta with A matrix.
Delta with A matrix. Okay.
This equation is nothing but pi of delta. Okay,
Okay. Okay.
so replace delta with A matrix.
Okay.
That
Hmm.
is your pi of A. This one.
Okay. And now now we have to find the
Okay.
alpha 1, alpha 2, alpha 3 value.
Yeah. So here, just a minute. In this, okay. First, you know your A matrix. Okay.
Okay. Okay.
So find delta I minus A.
Hmm.
Okay. So you will get polynomial in delta. Correct.
Okay.
So this is nothing but pi of delta.
Okay.
Okay, then this is nothing, replace delta with A, you will get this.
Acha, we will replace then delta with A. Okay.
Yeah, so let me show you one example because I don't have much time to discuss that so that you'll understand better way. I'll share this example also with you.
Okay.
Yeah, here you can see. So this is for Ackermann formula. Okay,
Hmm.
so A matrix, B matrix is given. This is our formula. Okay,
Okay.
okay, so this is the C matrix.
Okay.
Okay, so you are finding the C matrix. C and M both are same.
Hmm.
Okay, so then for the closed loop system for the desired poles.
Hmm.
Okay, this is the equation you got.
Hmm.
Okay,
Yes.
so now replace S with A matrix. You're getting pi of
Yeah.
A.
Hmm.
So S with A matrix, you're getting pi of A. Okay,
Hmm.
So that's what the calculations leads to this. Okay, so
Okay.
let me explain you clearly. Yeah, so now this is the matrix given to you. This is A matrix, this is B matrix. These are desired. Okay.
Hmm.
Okay, in the similarity transformation, that is method 2 in our case. Okay,
Hmm.
so this will be K1, this will be K2, this will be K3. Okay, so first what you do is you find the controllability matrix B, A, B, A square B. Okay, you're finding A, B, A square B. Then controllability matrix is B, A, B, A square B. Okay, yeah, det is equivalent to -1, which is not equivalent to 0. Hence, the system is controllable. Okay,
Hmm.
that is first thing. Next, what you do? So, for the open loop system, you find Si minus A. This is the characteristic equation.
Hmm.
Okay. Now, for the closed loop system, because these are the desired characteristic equation. Okay.
Hmm.
Now you have one polynomial here, another polynomial here. Okay.
Okay.
So from here you are getting A1, A2, A3. From here you are getting alpha 1, alpha 2, alpha 3.
Hmm.
Okay. Since the
Okay.
system is canonical CCF form, T inverse equivalent to I, the identity matrix. Now your K matrix is this: alpha 3 minus A3, alpha 2 minus A2, alpha 1 minus A1. Okay. So this is the K matrix. Okay. That is first one. Second one I told you. So what you do, this is the controllability check as usual. Okay. Next, with the desired closed loop poles, okay, you find this polynomial. Okay. So once you have this polynomial, replace S with A. So you will get A cube plus 7A square plus 12A plus 10I. So you'll be getting the pi of A. Is that clear?
Hmm.
Oh,
Okay.
yeah. Once we have pi of A, this is our formula for finding K.
Hmm.
Okay, 001 C inverse pi of A.
MBC no हाँ ठीक
Yeah,
okay.
so substitute in that. Find the C inverse. This is C inverse. So you'll get the K as this. 001 C inverse pi of A.
Hmm.
Okay.
Yes.
Next, the last method is, it is direct method. Again, state controllability check. Okay. So using the desired poles, okay, you get this polynomial. Okay. Now you are substituting this. This is nothing but Si minus A minus Bk. Okay. So this matrix you will get.
Hmm. Okay sir.
Okay. Then take the det of this. So this is the polynomial. Okay.
Hmm.
Now you have desired polynomial. You have A minus Bk polynomial. Compare the coefficients. So k plus 3 is equivalent to 7. K plus 2 is equivalent to 12. K1 equivalent to, sorry, K plus 1 equivalent to 10. Okay.
Yes sir.
Yeah. So then you will get your K1, K2, K3. Again 9, 10, 4. Okay. So three methods you can use for to place the desired poles in the S plane, which is called as the pole placement technique. Okay. So for the pole placement technique, before designing, you have to check the controllability. You have to consider this controllability matrix B, A, B, A square, etc. B, and make sure that, so we have, it has to be controllable. It means that it needs to have the full rank. It means that the data has to be equivalent to non-zero value. Then only we can say that system is totally completely controllable.
You have gone through the
Okay, then you can use any of these three techniques to place the closed loop poles in the desired locations.
so what you should I discuss
Hmm.
Okay, so that's the intention. Okay, so similarly, we here we are checking the controllability before we go for the pole placement technique. Okay, next class, what we do is we will discuss the observer design. Okay, what we do is we will first verify the observability, then we go for the observer design.
Saturday
That we will see in the next live session. Are there any doubts? Other
coming
doubts?
also if you want we can discuss. Then
Yeah.
Monday
Okay, sir.
Wednesday
We will.
and upcoming
Yeah. So if you're having any doubts, I'll be sharing these problems also.
Yeah, we
So
will.
if you
I will
please
try.
go
I
through them. If you're having any doubts, you can ask in the space.
next Saturday
Hmm. In the
Okay.
space.
Yeah.
The next class would be on
Observer
day after
design.
tomorrow. Friday.
Yes. Yes.
So
Friday.
Friday.
Friday on observer design. Okay. Yeah.
On what you just said?
you will let me know prior. I
Yeah. We'll have live session on 1:30. Okay.
Huh.
Friday.
Hmm.
will discuss.
Okay.
Oh, 1:30.
So
Oh,
we
sorry. Not 1:30.
Oh, it's
4:30.
4 p. Huh. It's
Yeah.
4.
Yeah.
Hmm.
Yeah. Yeah. Okay. Thank you.
Thank you, sir. Good night.
Thanks a lot.